Chapter 6, the Periodic Table. Section 6.1, Organizing the Elements. Here's our key objectives, so write these down. Explain how elements are organized on the periodic table. Compare the early and the modern tables, and identify three broad classes. Now put these down in your notes. At the end, go back and make sure that you can answer these. There might be a quiz on these things. Just make sure you're ready to do it. All right, so let's talk about, excuse me, talk about how this all started. Back in the 1700s, there were only about 13 known elements. So, it wasn't really important that we had a big way to organize them all. It was pretty easy to just memorize what they were. But as we got better in science, we started discovering more and more of them. So the number of elements started to increase that they knew about, and they needed a way to put them into groups, to organize them, and to do that. So the first person to ever do this kind of organize these was a guy named Dobereiner, and he grouped them into triads, groups of three, and put them in there by similar properties. So that was kind of the first attempt. Probably the most famous person to do it was a guy named Mendeleev, Russian chemist, and did this about in 1869, and kind of came up with a table of elements, and he based it on different properties. Now here's what his table looked like. Kind of look like that, and you can see that it doesn't have as many as we do, and this table is kind of sideways from how ours is. So you would kind of what we think of as columns going up and down, his are rows going across there. So what he did was he grouped them according to repeated properties. So for instance, if you looked at, let's say you look at Be number 9, and you go across, then you got magnesium, you got zinc, and you got cadmium. And he put them in that order because, those four had similar properties, so he kind of grouped them together. He also grouped them according to their atomic mass. Now, if you look at those numbers, you'll see they're close to the atomic masses that we have on our chart, not the atomic numbers. So that's how he did it. And if you also notice, you'll see some question marks on the table, and those are spaces that he left to be filled. He thought there were some elements missing. He actually predicted that there would be some elements found in between there. One of those that he predicted was germanium. He called it ecosilicon, and made predictions on its boiling point, melting point properties, and it was very, very close on many of those things that he did. When he was putting these together, he had a couple of them, tellurium and iodine, that didn't really follow if he followed the atomic mass. So he actually put them out of order, put them in a different order. He matched them up more by properties than he did by the masses themselves. And, it comes to, the modern table, that's exactly how we did it. And all of this was done before they knew the idea of the atomic number. So he's placing them in order based on properties, based on masses, but he'll move them if he needs to. And it ends up being, perfectly right order according to atomic mass, or atomic number, which wasn't determined until like 1913 when Henry Moseley figured out how to do that. Now, in the modern periodic table today, we put them in order by atomic number. If you notice, it goes from 1 through whatever, 110 or whatever it is. And, that's the atomic number. That's the number of protons that are in each element. And that's how they're arranged in there. So here's the periodic law. It simply states that if you arrange these elements in order of increasing atomic number, you have a periodic repetition of their physical and chemical properties. So you put them in order by number, and there's a repetition. In other words, all of the ones in one group have similar properties to those in another group. So if we're looking at this chart here, for instance, let's say you're looking at that second group, that second column there, Be, Mg, Ca, Sr, Ba. They all have similar properties. They're grouped in that particular way that they have that. All right, so let's talk about the divisions on the periodic table. There are three main things: metals, nonmetals, and metalloids. And if you look at the periodic table, you'll see across the top you'll see, at least on the ones that I'm showing you here and in our book, there's 3 labels. I think the one in the back of the room has 2. The red is the U.S., it's what we'll use. The blue is what they use in Europe. We'll never use that. And occasionally we'll use the IUPAC one, which is in black. So if you take a look at that chart again, notice the red's the ones that we use. So, Group 1A, that's the first column there. Group 2A, then 3B, 4B, and so on. The black numbers across top just run from 1 to 18, and that's the IUPAC method. And the blue is the European method, and we don't use that one. All right, so there's 3 classes. We've got metals, nonmetals, metalloids. And if you look at the chart now, you'll see that the metals, those are the yellow ones, and there's quite a few of those. Metalloids, there's a few of those, all in that kind of that zigzaggy line there. And the nonmetals in the upper right-hand corner. Hydrogen, of course, kind of in the wrong place as far as metals and nonmetals. So you got to think of it as a nonmetal on the right-hand side, even though it kind of has properties like the Group 1A ones do there. If you go across the period, from left to right, the elements become less metallic and more non-metallic. So, for instance, if you're looking at, let's say, lithium, Li, that's a pretty metallic element. If you get to boron, that's number 5, that's less metallic. Keep on going to neon, that's very non-metallic, okay? The metals, most of the table is made up of metals, about 80%. That's the ones on the left-hand side. And metals are always good conductors of heat, electricity. They have good luster. In other words, they're shiny. Most of them are solids at room temperature. The one exception to that is mercury. They're also ductile and malleable. Ductile means I can pull them into a wire. Malleable means you can pound them into sheets. So think about it. You can take metal and you can pound on it with a hammer and it doesn't break. It just bends, changes its shape, but it doesn't break. The nonmetals have a much bigger variation than the metals do. Metals are pretty similar. There's a lot of similarities between them. Nonmetals, quite a bit of difference between them. I mean, you've got a lot of different states. You've got some that are gases, a couple that are even solids, and you've got a liquid. So you've got kind of all of those states in there at the same time. They're usually not good conductors of heat or electricity. Carbon maybe is the one exception to that, but most of the other ones are not good conductors. And they usually tend to be brittle, so if you have them in a solid state and you try to pound them with a hammer, they're going to break or shatter. You're not going to be able to bend them. They're just going to break in half. And then the metalloids are kind of the ones in between here. So they're along that stair-step line in the periodic table that we saw. And they have some properties that are like metals and some that are like nonmetals. And at times they'll act like metals, and at times they'll act like nonmetals. And a lot of times it'll depend on like the temperature. And that's a very good property that we use. That's why we use things like silicon and germanium in semiconductors in computers and stuff, because they will change whether they conduct or don't conduct. So that's a good property for them. All right, there you have section 6.1. Make sure that you put in your notes the answers to the beginning, the objectives there. Explain how the elements are organized and compare the early and modern tables, and identify 3 broad classes. So just kind of jot some notes about those, make sure you understand all that particular stuff.